So today we have another class of operating system in this series, Mastering Concepts for GATE 2023, and the topic is Dining Philosophers Problem and its Solution. So first we are going to discuss its problem and then we will be talking about the solution. So guys, start sharing, keep sharing. Yes, Tushar, good evening. Welcome all of you. Guys, do share this session with all your friends in all Telegram and WhatsApp groups, so that we can have maximum students and they can take the benefit of this class. And do like the session also. So today we will be discussing Dining Philosopher Problem and its solution. So let's proceed. Before starting, let me introduce myself. My name is Anshul Sharma. I have 2+ years of teaching experience. In GATE 2020, I have secured All India rank 294, cleared ISRO and NILET exams, mentored more than 1,000 students as of now, and these are my area of expertise: operating system, digital logic, compiler and computer organization. Yes guys, do like the session and share as much as you can, because this session is going to be really interesting. Okay, and also one more thing, let me tell you that if you want to get the PDF of all my YouTube classes, you can join this Telegram group. Okay, you can just search it in the Telegram. You will be getting the PDFs. If you have any doubt in any subject, you can ask in this group also. And if you need any guidance related to your GATE preparation or related to the admissions, then also you can reach out to me through this group. Good evening, Aniket. Welcome. Yes. So shall we start now? One more thing, those who are not aware of this, that BYJU'S Exam Prep, we have started this free online YouTube course, that is Mastering Concepts for GATE 2023, for all these branches: mechanical, civil, computer science, electrical and electronics and communication. And this is going to be the schedule for all these branches. So in this series we will be completing the most frequently asked and most important, most difficult concepts in this series. Okay, so let's start guys. A Dining Philosopher Problem and its Solution. Good evening, Jaideep. Welcome all of you. So let's start it. So first of all, before even discussing this code and everything, we need to first understand what is this problem. Yes, Anshuman, where we can watch previous live sessions. So we have maintained one playlist in this channel, BYJU'S Exam Prep YouTube channel. You can see that for operating system we have maintained the playlist. The previous sessions, the entire sessions, you can see in that playlist. Okay, later on after this session you can watch that. And if you need the links for those sessions, so already I have shared in my Telegram group. You can join the Telegram group. There you will be getting the links of all my previous conducted sessions in this series. Okay, now let's talk about this Dining Philosopher Problem. So in this problem we have 5 philosophers. So there is one circular dining table here. Okay, yes, already shared. Arey yaar, this is the link na. This is the link. You can just search it in the Telegram, CS_by_Anshul_ Sir. You will be getting that group, and there I have shared all the links of my session. Now carefully pay attention here and see this Dining Philosopher Problem. So we have a circular round table here. Now we have 5 philosophers sitting on this round table. Okay, and the task of philosophers is only to either they are going to think or they are going to eat, right? And here we have the rice ball. So rice ball is not common. Every philosopher is having its own rice bowl. Okay, every philosopher is going to have its own rice bowl, but here I have shown it like, okay, there is one. Now for every philosopher, when let's say P0 philosopher, if it wants to perform eating operation or eating task, in that case it has to pick both the forks F0 and F1. That means for one philosopher we have you can say fork or you can say chopsticks. So we have 2 chopsticks for one philosopher. One is on the left hand side, other one is on the right hand side. Good evening, Shama. So if one philosopher has to perform eating operation, in that case first it has to pick the left fork and then it has to pick the right fork. Okay, one more thing, one philosopher cannot pick both the forks at the same time. That is not allowed here. Similarly, if let's say P1 wants to perform eating operation, in that case it has to pick F1 fork first and then F2 fork. Similarly for P2, similarly for P3, similarly for P4. Clear? And this is the code we have for philosophers. All the philosophers are going to execute this code here. Clear so far? Now what is the problem here? The problem here is, let's say if we are talking about P0 process or P0 philosopher, if it wants to perform eating, now due to this adjacent philosophers, as you can see, P0 is there and P1 is there. So if we are talking about the adjacent philosophers, if they want to perform eating operation, in that case race condition would be there. In that case race condition would be there. What is the race condition? So the order of execution of processes, or you can say the final result, will depend on the order of execution of processes. That is race condition. So here we will be facing a race condition if adjacent philosophers will want to perform eating. How it is so? Let's consider one case. Let's say we have a P0 philosopher and it is executing this code, while true, always true, thinking. Now after this one, it is going to pick the fork, take fork I. Now this I is same as the philosopher's index. So here we have P0. So here the value of I will be 0 here, and the value of here I plus 1 mod n will be, what is n here? N is number of forks. N is number of forks here, right? So I value will be 0. So we can say first it is going to pick its left fork, that means F0 here. So it is going to pick F0 fork here, first one, and then let's say it got preempted. Let's say it got preempted. Philosopher P0 got preempted. Now let's say P1 arrived. P1 arrives. So it is going to pick its left fork, that is F1. So for take fork, index value will be 1 here. So it is going to pick F1 fork. Now let's say P1 is going to pick its right fork. So here take fork I plus 1. So I value is 1. 1 plus 1 mod n. N value is 5. So it is going to be 2 only. So now it is going to pick its F2. So what happens here is, first we started with the P0 and it picked its left fork, but after that it got preempted and P1 arrived, and P1 has picked its left fork, which is the right fork of P0, So what will happen now in this case? First P1 will execute, because if it wants to perform eating, it needs both the forks here. So it will eat, and then it is going to place both the left and right forks on the table, and then this F1 will be used by P0 process. So race condition is there. Is it clear so far? This is the problem when we are going to have the adjacent philosophers performs eating process. Okay, now to eliminate this problem, or to have synchronization between the philosophers, what we need to do is, we have used semaphores here. So as you can see, now here in this case, this is the changed code. Here we are going to use the semaphores. So carefully say this, we are having the array of semaphores here. So let's say if we have a P0 philosopher, so for that we are going to have S0 semaphore, S1, S2, S3, S4. So total 5 semaphores we are having. Now what we are going to do here is wait take fork S of I. So whenever P0, let's say we are talking about P0 process philosopher here, it is going to perform wait operation on SI, So initial value of all these semaphores is 1. So these are binary semaphores, or you can say mutexes. So initial value of these binary semaphores are 1. Now first of all, P0 will perform wait operation on SI. So it is going to make it 0. And it is going to pick its left fork. Clear? Now let's say it wants to pick its right fork. So in that case, it is going to perform its 0 plus 1 mod n. That means 5, it is going to be 1 only. So now it is going to perform wait operation on S1. So it is going to make it 0. So now it has F1 also. Let's say while it is performing eating, let's say P1 process also arrived. Now what will happen? P1 process, if it tries to execute this statement, wait of take fork SI. Here I value would be 1 for P1 philosopher. So it is going to be S1 here. It is going to perform the wait operation on S1, but already the value of S1 is 0. Already the value of binary semaphore S1 is 0. So here it will get blocked. P1 will get blocked here. P1 will get blocked here. So that is why we have used the semaphores here to have synchronization between the processes. Is it clear so far? If you have any doubt here, please ask. Anyone? If you have any doubt, please ask. So this is semaphore is we have the array of semaphores here, and the indexes, or you can say the value is S0, S1, S2, S3, S4, total 5 semaphores we are having. So we have considered the indexing in such a way so that we can relate it with the philosophers. Is it clear? So in this way we can have synchronization between the philosophers here. Now P0 will perform eating operation, and after that it is going to signal the value of Si and Si plus 1 mod n. That means it is again going to make it 1 here after performing eating, and this one also it is going to make it 1. Now P1 can perform wait operation on Si, so it is going to make it 0. Right, this is done. So F1 will be accessed by P1 philosopher, and then it is going to make it 1 plus 1 mod 5, that means 2 only. So it is going to decrement the value of S2 and it is going to access F2 fork. So in this way we can maintain the synchronization between the philosophers in this dining philosophers problem, and this is the solution we have. Now there is one more thing we need to discuss here, is that there is a possibility of deadlock here. There is a possibility of deadlock here. How it is so? Carefully see this. Let me just erase this little bit. Now carefully see how we can have the possibility of deadlock here. Let's say we have process P0, philosopher P0, philosopher P1, philosopher P2, philosopher P3 and philosopher P4. So we have P0 to P4 as the philosophers. Now carefully see this. When P0 is executing this code, so for that we have 2 semaphores. One is your S0 and other one is your S1. Right, because the index is going to be same for the left fork, so it is going to perform S0 here and S1 here. It is going to perform wait operation here. Now for P1 it is going to be S1 here, and here it is going to be S2. For P2 it is going to be S2 here. For P2 it is going to be S3. This semaphore we are using for the left fork, this semaphore we are using for the right fork by P0 philosopher. Similarly here for P1 philosopher, similarly here for P2, for P3 S3 here, S4 here, for P4 S4 here, and here it is going to be 4 plus 1 mod 5. 4 plus 1, that is 5. 5 mod 5 will become 0. So this is going to be 0. Now we are considering one case when we can have a deadlock in this solution. Okay. Now we know this S1 value, S0, S1, S2, S3 and S4. All the values are initialized to 1 because they are binary semaphores. We are using it. So we have initialized the values of binary semaphores as 1. Now consider this case carefully. When P0 is executing, let's say it is performing, it wants to pick its left fork. So it is performing wait operation on S0. So it is going to make it 0, correct? Let's say it got preempted. Let's say P0 got preempted. Now P1 arrives. It is going to perform, it is going to pick its left fork. So it is going to perform wait operation on S1. So it is going to make it 0. Let's say P1 also got preempted. Now let's talk about P2. S2, it is going to make it 0, performing wait operation. Let's say after that it got preempted. Now again P3, it is also going to make it 0, and let's say after that it got preempted. Now what about last one, P4? So it is also going to make it 0, and S4 is 0 now. Now to pick the right fork. Now if P4 wants to pick the right fork, in that case it is going to execute S0. It is going to perform wait operation on S0. Yes or no? Clear? So if it wants to perform wait operation on S0, already you can see the value of S0 is 1. So here it is going to get blocked. Here it is going to get blocked. P4 is blocked. Let's talk about other processes. What about P0? S1 value is already 0. P0 is also blocked here. It will not be able to pick its right fork. That means it will get blocked at this statement. What about P1? Here also S2 value is already 0. P2 is also blocked. Similarly, S3 value is 0. P3 is also blocked. S4 value is 0. P3 is also blocked. So as you can see, all the processes are blocked. None of the processes will be able to make the progress. So if there is no progress, you can clearly see circular wait. Yes, circular wait condition is there because P0 is waiting for S1, which is held by P1. P1 is waiting for S2, which is held by P2. P2 is waiting for S3, which is held by P3. P3 is waiting for S4, which is held by P4. So circular wait is there. So circular wait is there and none of the processes are able to make the progress. So you can clearly say deadlock. There is a case of deadlock and this is that case. Okay. So in this solution that we have proposed, yes, there is a possibility of deadlock. There is a possibility of deadlock. Is it clear, everyone? If you have any doubt here, please ask. So deadlock possibility is there. Now, what are the solutions that we can propose to eliminate this case of deadlock? So there are 2 to 3 solutions that was proposed. One solution is, instead of allowing 5 philosophers to sit on the dining table, what we can do is we can eliminate, let's say, 1 philosopher. We are just allowing 4 philosophers to sit on this dining table. Okay, and we are keeping the number of forks as same. Now what will happen in that case? If instead of 5 philosophers we are just allowing 4 philosophers to sit on the dining table, in that case, let's say P0 is picking its left fork, that is F0, right? Let's say P1 is picking its left fork, that is F1. P2 is picking its left fork, that is F2. P3 is picking its left fork, that is F3. Now, as there is no P4, so definitely this F4 is also free for P3. So it has already picked its left fork. Now it can pick its right fork. So in this case, P3 will be able to perform eat operation completely. After performing this eat operation, it will place both the forks on the table. So when it places both the forks on the table, in that case, P2 can pick this F3. It will also perform eat operation, and then also it will place both the F2 and F3 forks on the dining table. After that, P1 can perform, because F2 is free now. So P1 can perform eating operation. It will place it. After that, F1 is free now. So P0 can also perform eating operation. So all the processes will be allowed in that case if we are just having 4 philosophers instead of 5 philosophers. So this is one of the solution that was proposed to eliminate the case of deadlock here. Is it clear so far? If you have any doubt, guys, please ask. Anyone having any doubt? So this is one of the solution. What is the next solution we have? There is another solution, that is, what we can do is we can say odd number of philosophers. We are writing the code in such a way that odd number of philosophers will first pick their left fork and then the right fork. Okay, and even number of philosophers will first pick their right fork and then the left fork. So let's consider this case as well. Now we are having 5 philosophers, but we have changed the condition. So odd number of philosophers and even number of philosophers. So this is odd, and let's consider this is odd. We have even number of philosophers, so E is here, even number of philosophers. Okay, this is also even. Fine, odd. So odd number of philosophers will first pick their left fork and then the right fork. But what about even? Even will pick first its right fork and then the left fork. So in that case, what will happen? Let's say P2 will be able to first pick this F3, right? P1 will first pick its F1. So that means this F2, which is common between P1 and P2, either P1 will be able to pick this or P2 will be able to pick this. So whichever philosopher will pick this first F2 fork, that will be able to perform eating operation. Simple. Is it clear? So in that case, there will be no deadlock, because ultimately, as you can see, P1 is picking F1, P2 is first picking F3, its right fork first. Now this F2 will decide whether P1 will be first performing eating or P2 will be first performing eating. So there is no chance of circular wait now. There is no chance of circular wait now. So P1, if P1 picks first, then P1 will perform eating. If P2, this philosopher P2 will pick F2 first, then P2 will perform eating operation. This is another solution. There is one more solution. Let's talk about that now. There is one more solution, and that solution is what we are going to do here now. We have P0 philosopher, we have P1 philosopher, P2 philosopher, P3 philosopher. Let's say these 4 philosophers will first pick their left fork and then the right fork. But the last philosopher which we are having, that is P4, that will pick first its right fork and then its left fork. So that means for the last process we are making some changes in the code, or you can say last philosopher will execute little different code. That first it is going to pick its right fork and then its left fork. For all other processes, they will be picking first their left fork and then the right fork. So what will happen in that case? Let's analyze that problem also. So here we have these cases. Just in the last one, what we are doing here, carefully see this. We have P4 here. So instead of first picking left fork and then the right fork, we are interchanging these two statements. First it will pick its right fork, which is S0. It is going to perform wait operation on S0, and then it is going to pick its left fork, which is F4. That means it is going to perform wait operation on this semaphore S4. Now what will happen? It got blocked. S0 value is 0. It got blocked. S1 value is 0. Preemption S2 value is 0. P3 preemption S3 value is also 0. Now this is not 0 as of now. Let's write S4 as 1. Now carefully see this. P4 will perform S0. P4 will perform wait operation on S0. S0 value is already 0. That means it will be blocked here. P4 will get blocked here, right? P4 will get blocked here. Now let's come back to P3 philosopher. P3 S4 value is still 1. That means it is going to perform wait operation 0. P3 will perform eating and it will place both the forks back to the dining table. And then what about P2? S3 value is 1. When it is going to place it back, the value will become 1. P2 will be able to execute wait operation on S3. It is going to make it 0. So P2 will also perform eating operation and it is going to place it back. So it is going to make it 1 because signal operation it is going to perform both on S2 and S3. So we are going to make it 1. Now S2, S3, S4, all the values are 1. Now it's time for P1. It will perform wait operation on S2. It will perform the eating and it will make it 1, both S1 and S2. So P1 is also done. Now P0, S0, S1. So S1, it is 1. So it will make it 0. It will perform eating operation and then it is going to place it back. So it is going to make it 1. And then at the end, S4 can also perform waiting operation on S0 and S4. S0 and S4. It will perform waiting operation and then it is going to place it back. That means there is no deadlock here. Clear? So 3 solutions. First solution is, instead of allowing 5 philosophers to sit simultaneously on the table, we are just allowing 4 philosophers to sit at the same time. This is the first solution to eliminate the case of deadlock. Second condition is, odd number of philosophers will pick first their left chopstick or left fork and then the right fork. Even number of philosophers will first pick their right fork and then the left fork. This is the second solution. Third solution is, the last philosopher will pick first its right fork and then the left fork. Remaining other philosophers will pick their left fork first and right fork then after that. So these are the 3 solutions that we can propose to eliminate the condition of deadlock. Now is it clear to all of you? Yes, Subrajit sir, if odd numbers pick first right and then even first left, will they be deadlock? So you are saying if odd number, yeah, you can do that also, right? Vice versa is also true now. If odd number of philosophers, they are picking right fork and then the left fork, and you are changing the condition for even also. First they are picking left and then right, so that is also valid, na? Okay, vice versa is also true. Fine. So now we have one question based on this. It is not exactly, but yes, almost you can say it is based on dining philosopher problem only, because the question is arranged in such a way that you can just get a clear idea how to solve this and what will be the answer. So I want all of you to try this question and let me know what should be the answer. So basically, by proposing these solutions for deadlock, the remedies for deadlock, we are trying to dissatisfy the condition of circular weight. That's what we are trying to do. Because if there are 4 conditions for deadlock, necessary conditions, one is mutual exclusion, second one is your no preemption, third one is hold and wait, fourth one is circular weight. So if you can dissatisfy any one of the 4 conditions of deadlock, necessary conditions for deadlock, in that case there will be no deadlock. So by proposing those solutions, those remedies, we are trying to eliminate, or we are trying to dissatisfy circular weight here. Now try to solve this question and let me know what should be the answer, guys. So here option A is a thrashing. I hope you know what is a thrashing here. Thrashing is not related to this one. It is the concept which we talk about in memory management unit. Basically thrashing is, you can say, when the number of memory accesses almost becomes equal to the number of page faults. That means whenever you are accessing the memory, then you are facing page fault. So that condition, that situation becomes thrashing. So you can clearly eliminate this, that there is no possibility of thrashing here. They have just mentioned directly. This is one of the previous year question. PYQ. In all the sessions, those who have missed my previous sessions, do watch it, because after explaining the concept, I have taken PYQs also based on the entire synchronization. And also the next session that we have day after tomorrow, in that only PYQs will be there. Remaining PYQs I will take and try to solve for all of you. And then after that we have just last session, that is Menti quiz. Menti quiz will be there. So 23rd and then we have 25th. 23rd we have session and then we have on 25th. Yes, anyone getting the answer for this question? Yes. That's why I'm saying it is same. It is based on that only. The code is based on that only. Okay, let's see here. Let m of 0 up to m of 4 be mutexes, that means the binary semaphores, and p0 to p4 be processes, right? In place of philosopher, you can replace the philosophers with processes. Suppose each process p of I executes the following code. This is the code every process is going to execute. This could cause thrashing, deadlock, starvation, but no deadlock, none of the above. So let's see here. We have one process P0, we have one process P1, P2, P3 and P4. So P0 to P4 we have processes, and we are performing wait operation on m of I, then wait operation of m of I plus 1 mode 4, and then release means signal operation we are performing. So here for P0 it is going to be M0, and here it is going to be M1. For P1 it is going to be M1, and here it is going to be M2. For P2 it is going to be M2, and here it is going to be M3. For P3 it is going to be M3, and for P3 this is going to be M4. 3 plus 1 mode 4 0. This is going to be 0, not M4. This is going to be 0, because 3 plus 1 mod 4 will give you 0. 3 plus 1 4, 4 mod 4 is 0. For P4 it is going to be M4. And what about this one? 4 plus 1 5, 5 mod 4 will give you 1. So these are the mutexes that is accessed by these processes from P0 to P4. Now carefully see this. As the values of these mutexes, initial value of these mutexes are 1 initialized. Okay, let's say P0 executes. It is going to perform M0. It is going to perform wait operation on M0. It is going to make it 0. Let's say it got preempted. Now P1, M1 got preempted. P2, M2 got preempted. P3, wait operation on M3 got preempted. Now let's say P4. So here P4, it performs M4, right? It performs wait operation on M4, fine. Now it wants to perform wait operation on M1. But here if you see, already P1 process has performed wait operation on M1. That means P4 will get blocked here. P4 will get blocked here. Yes or no? Let's talk about P3. M0 already performed by P0, blocked here. Okay. Similarly, P2 already M3 performed by P3, blocked here. That means all the processes will get blocked. All the processes will get blocked. So there is no progress. So clearly we can say none of the processes are able to make the progress. So we can say deadlock is there. Deadlock is there, because when deadlock is there, there is no progress. Clear? Deadlock implies no progress. So option B is the correct answer. Starvation but not deadlock, that is incorrect. Option D, none of the above, that is incorrect. Clear? Now if I ask you, if I want to eliminate this possibility of deadlock in this code, so what to do now? Yes, everyone. If I want to eliminate the possibility of deadlock in this code, the best thing would be change the code for this P4 process. First perform this one and then this one. So we can interchange these two things. We can interchange these two things, these two statements. First P4 will perform this one, wait on this one, and then wait on M of I. That means we can interchange these two things. If we do so, like M1 here and M4 here, then in that case already wait operation P1 has performed on M1, so P4 will not be able to perform here, it will get blocked here, and then all other processes will be able to make the progress here. They will be able to complete the execution. Then later on at the end P4 can also make the execution, okay, complete the execution. So in this way we can avoid the possibility of deadlock. But as per the question, yes, deadlock is there. Deadlock is there. This could cause deadlock. So I hope it is clear to all of you. So that was Dining Philosopher Problem and Solution, and we have solved one question based on that also. Now we have the next class, that is day after tomorrow on 23rd. Okay, on 23rd we have the class. So guys, if you want to get the PDF of this class, you can join this Telegram group if you haven't joined it. Next class we have on 23rd. So we will be solving the remaining PYQs. We will try to solve most of the PYQs in that session. And on 25th, we have the Menti quiz based on synchronization. So these are the last two classes. After that, another subject is going to start, and that will be taken by Satya Sir. Okay, C programming and data structure. Yes, it's okay, Subrajit. Okay, so thank you all of you for joining this class. We'll see you in the next class. Till then, take care and bye-bye. And before leaving the session, do subscribe to Byjus Exam Prep YouTube channel so that you don't miss any notifications of our technical classes as well as general sessions that we are conducting for you for GATE 2022 as well as GATE 2023 students. And also press the bell icon so that you get the notifications. Okay, thank you all of you. Good night, take care and bye-bye. Thank you all.